We've seen how scatter plots show the relationship between two variables, and straight line relations are important because they're common and easy to interpret. We've also put regression lines in our scatter plots and used those to help us see how strong or weak the straight line relation is. And we call the relation strong if the points all lie close to the regression line, and weak if they are more scattered and spaced out around the regression line. So this is nice, but we want to have a more accurate numerical measure of how strong a straight line relationship is, and we're going to get that by using correlation, which is denoted with an R. The correlation measures the direction and strength of the straight line relationship between two numerical values. So correlation is a number, and it's always between -1 and +1. It's negative if the slope of a regression line for the scatter plot is negative, and it's positive if the slope of a regression line for the scatter plot is positive. Perfect correlation, if we have r equals 1 or r equals -1, occurs when all of the points in the scatter plot lie exactly on a straight line. If correlation is equal to 0, then that indicates that there is no straight line relationship. You just have a random cloud of points on your graph. So let me draw a little picture down here. So correlation values go between -1 and +1. At 0, there is no correlation, there's none. And then as you go out towards either +1 or -1, correlation gets stronger. At +1, we have perfect correlation, which means all of the points lie exactly on a straight line with a positive slope. At -1, we have perfect negative correlation, which means that all of the dots are on a straight line with negative slope. So a line that goes down as you go to the right. Let's look at an example. We're going to see a bunch of scatter plots on the next slide, and it's not always easy to guess the value of the correlation from a scatter plot. So for the pictures you see on the next slide, they all have the same scale for their x and y axis, so we can compare them easily. So here in my first picture, I have a correlation of r equals 0. So I've got no correlation, and I've just got a cloud of points out here. My next scatter plot has r is equal to -0.3, and you can kind of see that the points are more contained. They don't go outside of these dotted lines here. So I've got sort of a slightly negative correlation here. The points sort of go down as I go to the right, but they're still spread out a lot. In the next picture, my dots are a little more closely grouped, and you can tell in this picture that they're going up as I go to the right, so I've got a positive correlation of 0.5. It's kind of a mid-range. It's not very weak, and it's also not very strong. Now my correlation is getting even stronger, but in this graph on the lower left, we've also got a negative correlation, so the strip that my points are in is getting narrower and narrower, and in this one, the points go down as I go to the right. And in the bottom middle picture, my points get even more close to a line. They're in an even narrower strip. And again, I've got positive correlation because they're going up as I go to the right. And finally, I've got very strong correlation on the bottom right. It's a very narrow strip containing all of my points, and it's a negative correlation because they go down as I go to the right. So now we sort of have an idea of what correlation tells us, but we need to be able to calculate it for a data set. So if we have data on two variables, x and y, for n individuals, then if we know the means and standard deviations for those two variables, we can calculate the correlation, and it's given by this formula here. So if you look at one of these terms here, each of these is the deviation of a point over the standard deviation for that variable. So this is kind of a measure of how far away that point is from where we expect it to be. So we take that for each point in our data set, and then we add those all up and divide by n minus 1, and this gives us sort of an average of how far away the points are from where we expect them to be if they were all in a straight line. So you can sort of see what's going on here, but it would be hard to plug in the numbers into this big formula. So we have an equivalent formula, which is a little easier to work with in practice, and that's given here. So to find correlation, we need to know several things. You need to know the mean and standard deviation of the x values, and the mean and standard deviation of the y values. Also the number of individuals you have, which is n, and for each individual you need to know its individual x and y value. So then we take the products for each individual of their x value times their y value, we add those all up, we subtract n times the mean of the x values times the mean of the y values, and then divide everything times by n minus 1 times the standard deviation of the x values times the standard deviation of the y values. So let's look at an example of actually calculating the correlation. So here I've got my beer and blood alcohol example again. I've got this chart where each student was given a certain number of beers. The first student was given 5 beers, and after they drank the beers, their blood alcohol content was measured. And the first student had a blood alcohol content of 0.10. So here, the sample size is n equals 16, because I've got 16 students in my chart. The explanatory variable y we said was beers, and the explanatory variable x is beers, and we said the response variable y is blood alcohol content. So I'm going to give you the means and standard deviations for these here, so we don't have to do too much work for our example. And these are given to two significant figures. And that means that if we ignore any leading zeros, like these two zeros in my standard deviation of y, then I've got 2 digits after those zeros. Same thing if you look for the mean of y, I've got 2 leading zeros, and after that I have 2 digits. So we've got the number of individuals n, we've got the mean of the x values, the standard deviation of the x values, the mean of the y values, and the standard deviation of the y values. Now I need to find for each of these the products. So for the first one, x1 times y1, it's going to be 5 times 0.10, which is 0.50. For x2 times y2, I've got 2 times 0.03, which is going to give me 0.06. For x3 times y3, I've got 9 times 0.19, which is equal to 1.71. For x4 times y4, I've got 8 times 0.12, which is equal to 0.96. For x5 times y5, I've got 3 times 0.04, which is going to give me 0.12. And I just keep going and fill in the rest of the chart this way. I'm just multiplying the x values times the y values. And once I've done that, this is what I end up with. And the next step is to add up all of these products. So I'm going to add up 0.50 plus 0.06 plus 1.71 and go down my chart and add up all of those products. And if I do that, that's going to give me 6.98 is the sum of all those products. So now I have everything I need to plug into my formula for correlation. So this is my formula again. I've got all my products and I added them all up, and that gave me 6.98. And I subtract n, which is 16, times the mean of x, which is 4.8, times the mean of y, which is 0.074. And then I divide by n minus 1, which is 15, times the standard deviation of x, which is 2.2, times the standard deviation of y, which is 0.044. And that gives me 0.89 for my correlation. So that is pretty high. That is very close to 1. And for your homework or practice problems, I won't give you a set this big to calculate correlation for. You'll have fewer individuals in your data set, so it won't be quite as long of a process. So things you should know for this section: you should be able to find the correlation value R for a given data set with two variables. You should also understand what the correlation value says about the direction and strength of a straight line relationship. And that's really the more important part, is understanding what correlation values say. So if we have a correlation that is close to 0, then we know that the relationship is very weak. If the correlation is close to positive 1, we know that the relationship is strong and positive. And if we have a correlation that is close to negative 1, then we know the relationship is strong and negative.